All right, so as we have some students finishing some things up for me here, to start our lab that we're going to do a little demo lab today, what I would like for you guys to do is I would like for you to spend a little bit of time refreshing what we did yesterday. So this is specific heat capacity, bell work number 1. You're going to write down the equation. Q is equal to what? Tell me the units for these things. Specific heat capacity, what was that? What was the specific heat capacity of water? I have one practice question I would like for you to go ahead and do. I want to know the change in temperature of that. And then there is a little kind of scenario type question as well. So we're going to do this bell work, refreshing what we did yesterday, and then we're going to do a little lab simulation. Okay? Perfect. All right. You can leave it right there for right now if you want. Is that 60 mils? Put it in the cup for me. Yeah, just one. Bell work to make sure everybody's on the same page. So the first one, what is the heat equation? Q is equal to what? MC delta T. Q is the quantity of thermal energy or heat, which is written in joules, which is a J you will need for your final answer if you calculate Q. M is mass or grams. C is our new idea. It's called specific heat capacity. And then we have degrees C for our change in temperature. Remember, you subtract to get a change in temperature. Specific heat capacity is just the amount of energy needed to change the temperature of 1 gram of a substance by 1 degree Celsius. So I don't think of it as that big, long thing. I think of it as a cost to heat or cool. How much does it cost to heat something up? Is it a high cost or is it a low cost? And today we're going to see 3 examples of 3 different metals that have 3 different costs to heat them up. Okay? Water you have to memorize is 4.18 joules per gram degree Celsius. Every substance has its own specific heat capacity. Water just happens to be super duper 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 high and takes a ton of energy to heat it and to cool it. Okay, perfect. Let's do some math very quickly. You will have math problems on Friday for sure. Copper has a specific heat of 0.38 joules per gram degree Celsius. That is my C value. If a piece of copper with a mass of 538 grams had 35,000 joules transferred it, what is its temperature? So my question is, what is the delta T? Q is equal to MC delta T. Q is 35,000. M is 538. C is 0.38. And I'm looking for delta T. I'm going to bring 35,000 down here. I'm going to multiply these 2 things together to get 204.44 T. And then in order to solve, I just divide both sides, whatever's stuck to the variable. So 204.44, 35,000 divided by 204 gives me an answer of 171.2 or 19, depending how you round. Make sure you have a unit of degrees Celsius on there. Okay, does anybody have any questions on why I put which variable where, how to solve for this? We will do more practices of these, especially tomorrow, because you're going to have math problems on the quiz on Friday. Okay, perfect, perfect. All right, so you have a guest over. They take a really long hot shower. They empty your hot water tank. Can you immediately then take another shower? No. Okay, the problem with water is it has such a high specific heat capacity. You have to wait a long time in order to get that energy back into that water to heat it back up. Okay, that's why parents are like, I'm not paying that hot water bill, because it costs a lot of energy to heat up water because it has a very high specific heat capacity. Okay. All right. Good stuff. Okay. So today what we're going to do is we're going to do a little lab simulation. Okay. And so what we're going to see is we're going to see students kind of doing the lab that we would have done if you were in class, and then we're going to do the data together. So if you go to the next page, it says transfer of energy with metals and water. Okay, just a little reminder from last week. Heat is the transfer of thermal energy. So you're going to see some transferring of thermal energy going on here. All thermal energy goes from what to what? High to low. Very good. And then another little guy you might see on your lecture questions today. The good old law of conservation of energy says energy cannot be created or destroyed. So if our water gets hot today, okay, energy that was gained by water or gained by something, anything that gains thermal energy has to be lost by something else. So if our water gets warm, that's because the hot metal cooled, okay? So energy doesn't just come from anywhere. If something warms up, that means something gave it energy. All right, so what we're going to do is I have 3 samples of metals, okay? And you can see here it says, loop the string of each metal sample over a utility clamp, blah, 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 all that kind of good stuff. Let's break it down. Those of you at home, hopefully you can see. We have a sample of lead, okay? And those of you that are down with fishing, you're like, well, that looks like a fishing sinker. And you would be right. Okay, this is 30 grams of lead. It's a lead fishing sinker that's 30 grams. Then I have a sample of brass. Okay, it's just a kind of, it's been dull because it's been oxidized. But so here we go, brass. And then the last thing I have is a sample of aluminum. Aluminum. Beautiful. Now, these have loops around them because as the students can see here, we have them boiling over in boiling hot water. Okay, so that's the aluminum sample for those of you at home. So the procedure would go as follows. You loop the string around each metal sample, position it so it's in the 400 ml beaker, check. Heat the boiling water for 5 minutes after boiling. We've been in here for 10, so check. While the solid is being heated in a hot water bath, okay, get 60 mils of cold tap water. Our students got those, so check. After the object has been heated in boiling water for a full 5 minutes, record the temperature of the water in the styrofoam cup, and then quickly transfer the metal into the water and stir to ensure a complete heat transfer. So what I want you gentlemen to do is go to wherever your cups were. Go ahead. And everybody's going to follow along and write down this data. So I'm going to ask one at a time. We see my lead is the middle one. AJ, what is the initial temperature of your water? And your thermometer might have turned off. You might need to hit it back on. It's that button with a circle on it. Or do you got a number? Now it's all changing on you.
It says 20.5.
20.5 degrees for the lead, and you are aluminum. John, what is your initial temperature of your water?
20.3.
20.3, so that's the bottom one. And then, Sable, what you got?
22.4.
22.4. Okay, stay there. We got one thing. What's going to happen is they are going to take these metals out of boiling hot water. Let's think about this really fast. What temperature is water when it boils? 100 degrees, right? Those metals have been boiling for 5 minutes in 100 degree water. So what temperature do you think those metals are? They're at 100, right? And the water is in the 20s. So I want you to think about what's going to happen to the temperature of the water when they put a piping hot metal in it, and let's see what happens, okay? So what I want you guys to do, take your thermometers out, grab the styrofoam cup. I want you as quickly as you can to just grab the string and drop it into your water as fast as you can. Ready? We want to take that hot metal, grab the steering, and in the water goes. Good. Now put your thermometer in and give it a stir, and tell me how warm the water gets. It's kind of going to equalize out. Watching your temperature as it's going. Which direction should the water temperature go? It should go up. Very good. And once you kind of get a high, or it will kind of level off temperature, hit me with it. All right. 27 point.
Yeah, that's 27.
.0. Nice. 27.0. Sabo, what you looking at with the brass?
26.0.
26.0 with the brass. And Potter?
22.1.
Woohoo!
Actually, can you fix that?
Yeah, I can.
27.3.
Wonderful. All right. So Train, that's perfect. You guys can go ahead and sit down now. That would be great. And then you guys can get your data. Does everybody have this written down? Perfect. Chant, will you turn those off, the Bunsen burners off? We just don't need Bunsen burners flailing around for no reason. All right. So let's talk. The math can get very confusing. So what I want to do is I want to break it down into some chunks, and I want you guys to kind of be able to do some of the math and visualize it. So we had lead, brass, and aluminum. And if you start to look at the numbers, you can see that each of them changed the water a different amount, which is weird because they were all at 100 and the waters were all in the 20s, and I wonder why. And that might show us a little bit of the specific heat capacity we've been talking about. So I would like to put the information that we have down into this little infographic down here. We have the water in our lead started at what temperature? So the initial water temperature for lead started at 20.5 degrees. Okay. The initial water temperature for our brass started at 22.4 degrees. And what was the initial temperature for our water for our aluminum? Was 20.3 degrees. Do we all agree with that? Now, we just said that we put those metals in the water for 5 minutes to get them to what temperature? All the metals started at 100. Okay. They were boiling, boiling, boiling. So does everybody understand where it was right before we threw everything together? Okay. Water was cold, metal was hot, boom. Then what happened was the hot water gave some of its energy to the hot metal gave some of its energy to the cold water, and they kind of came together. Now, unlike the lab last week where we had hot and cold water together and they met right in the middle, this did not meet right in the middle, did it? And that's because of the different specific heat capacities on my materials. The final temp for the lead was 22.1 degrees. The final temperature for the brass was 26.0 degrees. And the final temperature for my aluminum was 27.3 degrees. Okay? So what you're going to need to know is how much temperature they changed. So grab your calculator here. We're going to do this real time. How much did my water warm up with the lead? Well, let's see. The difference between 20.5 minus 22.1, and I can turn on my camera. 20.5 minus 22.1, and you can take an absolute value. How much did my water warm up? 1.6 degrees. Okay. The lead warmed up my water 1.6 degrees. How much did the lead cool down, though? That went from 100 to 22.1. Perfect. 77.9 degrees. So did they meet in the middle? Absolutely not. Okay. One only warmed about 1.5 degrees, and one cooled down a whole bunch. Let's try the next one. Hopefully you can figure out what we're doing. We're just taking the differences of these two numbers. The brass warmed up my water. Let's do 22.4 minus 26. 3.6 degrees. And my brass cooled down 74 degrees. Does everybody see where I'm getting these numbers from? I'm just taking the difference to see how much their temperature changed. And let's see, 20.3, 27.3, well, that's easy. The delta T of the water for my aluminum is 7 degrees. And this one's perfect, 72.7 degrees. So now we have some math that's going to help us start to figure out how much energy was in these things, okay? I want to look at a few things very quickly. The lead and the aluminum and the brass all heated up a different amount. So in the post-lab questions, I want to come back to this. When you chuck the really hot lead in, it only warmed up the water 1.6 degrees. When you chuck the really hot brass in, it only warmed it up 3.6 degrees. And when you chuck the really hot aluminum, it warmed it up 7 degrees. So looking at the questions on the back, okay, based on your data of how much temperature the water changed, which sample do you think contained the most thermal energy? And I'm going to slip it back over here. You guys are on the back. Which metal do you think had the most thermal energy in it coming out of that hot water if these are the results you got? What do you think? Who do you think? Talk to me. Talk to me.
I think aluminum.
Yes, tell me why.
Because it increased
A whole
temperature by 7.
Absolutely. So that means my piece of aluminum here, even though they're all at 100, this one had more energy in it because it made the temperature go up the most. Okay, we had 60 mils and everything. They were all 100 degrees, but this got the temperature up higher. Fantastic. The aluminum, because it changed the water temperature the most. It changed the water temperature the most. Okay, awesome. Awesome. So with that, based on your data of how much temperature changed the water, which sample contained the least amount of energy? Anybody here? Which one would have the least amount of energy in it? Talk to me.
The lead.
The lead, because it only changed the temperature a little bit, right? Perfect. Very, 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 very good. Okay, you guys are thinking what thermal energy means. Okay, that is perfect. Now, we are going to calculate how much energy each of these gave to the water. So we're going to do some Q calculations here. So it said, using the heat equation, Q is equal to MC delta T, please calculate how much energy the water sample gained for each trial. And we're going to assume that 60 milliliters is 60 grams because the density of water is 1. Okay, so I think it's really good to start to kind of label our thing. We have Q of the water with the lead, Q of the water with the brass, Q of the water with the aluminum. But we got 60 grams of water every single time. We got 60 grams of water every single time. Okay. The other nice thing about water, what is always the specific heat capacity of water? 4.18. So those 60 grams of water always had a specific heat capacity of 4.18. So the only thing that was different was how much the temperature could change with each metal. So now you're going to kind of use your data from the other side. And I want to know the delta T of the water with the lead, delta T of the water with the brass, and the delta T. So instead you don't have to go back and forth, let me do this with you. So the first equation is going to have 1.6 as its delta T. The next one is going to have 3.6 as its delta T. And the last one's going to have 7 as its delta T. 1.6, 3.6, 7. 1.6, 3.6, and 7. Now, what I want you to do is I'm going to put the music on quietly, and I would like for you to just answer. We'll do 6 together. I would like for you to answer 4. Ooh, maybe we'll do 5. At least do the numbers to 4. Let's have you guys do 4 on your own. Can you tell me how much energy each of those samples gave? Beautiful. And I'll do mine too, and then we'll come together. Okay. Is everybody getting some numbers? And this is how many joules each of those cups of water gained. All right, all right, all right. Perfect. All right. Let's do them in here. Holler at me if I made a mistake. Hopefully we're good. I got the water with the lead sinker in it. Got 401.28. Unit needs to be joules. That's Q, joules. I got the water with the brass got 902.88 joules. Feeling good. And then, that aluminum had a lot of energy in it, like we just said, 1755.6 joules. Okay. That's how much energy went into that water. Now, this is probably a lecture question, so stay with me. It says, fill in the following data table with how much energy each metal sample lost. Well, the law of conservation of energy would say, if this is how much is gained by the water, where did that energy come from? Why did the water get hotter? Because the metal got cooler, right? So if the lead guy, if he gained 401 joules, that means the lead itself lost 401 joules. And if the brass water gained 902 joules, that means the brass itself lost 902 joules. And this is so it's like a little repetitive, but that's okay. If the water from the aluminum gained 1,755 joules, that means the aluminum itself lost 1,755 joules. Why? Because the law of conservation of energy says so. Whatever is gained by one thing is absolutely lost by something else. And this is going to drive our harder math next week. Okay? It's going to be all right, though. So, tying it all together, do these specific heat capacities make sense? And the answer to that is yes. Okay, aluminum has the highest specific heat capacity, and it also had the most thermal energy. Okay, it took the most amount of energy to get it to 100 degrees. So therefore, it had the most to transfer. Awesome. Okay. And then the lead had the least amount of energy needed to heat up because it had the lowest temperature change. So all we're trying to drive home to you is this is the cost to heat or cool. It took a lot of energy to heat the aluminum, and that aluminum made the temperature of the water very hot. It doesn't take a lot of energy to heat the lead, and it couldn't change the temperature of the water very much at all. Okay? How it feeling? We're doing okay. So just kind of giving you examples of specific heat capacities. And these types of calculations we're going to have to start doing here next week. We're not going to get that hard that fast. But what I want you guys to do right now is you have about 7 minutes. I want you to open up your Chromebooks. I want you to do the 3 lecture questions while we're right here in your head. Okay, feeling good. All of this comes directly from the lab. So if you want to have that lab out to answer those lecture questions, let's do it. Tomorrow we're going to practice for our quiz. And everybody's feeling good. Oh, there's more people here now. Let's put this music on. I'll come around if you guys have any questions here. Let's see who's here.